Hello everyone. So in this second part of the this important formulas and concepts for GATE 2023 exam for metallurgical engineering. So the next this one is interstitial sites. So for this cubic material we have a simple cubic, BCC and FCC. So in simple cubic we have a cubic as a interstitial sites which is present at the center of the unit cell. That location of this interstitial site is half. Now for BCC and FCC, the important interstitial sites are this tetrahedral and octahedral, and the number of tetrahedral sites in BCC is 12, and number of octahedral sites in this BCC is 6. While in case of a face centered cubic, the number of tetrahedral site is 8 and number of octahedral site is 4. So this number of tetrahedral sites is 2 times the number of octahedral sites. While in case of hexagonal closed pack material, the number of tetrahedral sites is 12 and number of octahedral site is 6. Now let's go to this next one, which is Bragg's law. So in GATE examination, this you can get one this numerical problem on this topic. So the this Bragg's law is n lambda is equal to 2d sine this 2d this sine theta, and for this first reflection, this n is equal to 1. So this formula become lambda is equal to 2d sine theta. While this lambda is this wavelength of the target material, and target material is of copper or chromium or cobalt, sometime it is molybdenum, like that. D is the interplanar spacing. So here you can see we have this one plane here, another plane here. So the distance between the two plane is called D here. And theta is the half of the Bragg angle. So Bragg angle is 2 theta. So this theta is half of the Bragg angle. So using this formula, this we should always take care. We have to use half of the Bragg angle here. That is the this theta here. Yeah, so that's all. This next one is point defects. So these point defects are thermodynamically stable defects. So there are these various types of these point defects are present, like vacancy, interstitial, small substitutional atoms, large substitutional atoms, Frankel defect, and Schottky defect. Next one is this vacancy concentration. So one numerical problem this you can get in this exam. So at room temperature, the concentration of vacancies is small, but the concentration of vacancies increases exponentially as the temperature increases. So in this formula, this you can see NB is equal to n exponential minus QB by RT. So when this temperature will increase, this whole value will decrease, but again you have minus sign here, so the complete this full value is increases. So this concentration of vacancy increases exponentially with increase of this temperature. So here NB is the number of vacancies per centimeter cube, N is the number of atom per centimeter cube, QB is the energy required to produce 1 mole of vacancies. So that will be in calorie per mole, this per mole or joules per mole. R is the gas constant, T is the temperature in degree Kelvin. This next one is Peierls-Nabarro stress. So this stress is required to move the dislocation from one equilibrium this location to another, and it is represented as tau is equal to C exponential minus KD by B. So here tau is the shear stress required to move the dislocation. D is the interplanar spacing between the adjacent slip plane. So a slip plane means this we know the maximum planar this planar density. B is the magnitude of the Burgess vector, and C and K are the constant. So this formula you can remember. You can get this one numerical problem on this. Next one is Griffith failure this criteria, which is generally useful for the this brittle this for brittle material. So this the Griffith theory states that a crack will propagate when the reduction in the potential energy that occurs due to crack growth is greater than or equal to increase in surface energy due to the creation of new free surface. And this theory is applicable to elastic material that fracture in brittle fashion. So here you can see you have an infinite plate, and if you have a center crack of length 2a, so this formula is written as sigma f is equal to square root of 2 this surface energy term, and this E is the elastic modulus divided by pi a. A is the half of the internal crack length. So this you can this important thing. So A is the half of the crack length. If in numerical problem it is given a surface length, this surface crack length A, so you have to use directly that A. But if it is given internal crack length, then you have to use half of the internal crack length here. So this thing, this you can remember here. Next is true stress and true strain and true stress. So basically, the difference between the engineering stress and engineering true stress is that in engineering stress we have to use this this original area like that. So if it is stress versus strain diagram, so this will be as engineering stress versus engineering strain. While in this true stress, we have to use the instantaneous area. So this stress strain diagram will lies always left and above like that. So this is for true, and this one is for engineering. So the relationship between the engineering stress and true stress is like that. The true stress is equal to engineering stress multiplied by 1 plus engineering strain. While the relationship between engineering strain and true strain is equal to logarithmic of 1 plus engineering strain. So this you can remember, one numerical you may get in the exam. Next one is the plane strain, this fracture, plane strain fracture, this toughness. So this is represented as K1C. One is here the mode 1 loading. One represent the mode 1 loading, and it is equal to Y. Y is here dimensionless geometry factor that is dependent on the geometry of the crack and the geometry of the part and this loading configuration. So if it is not given in the in your numerical problem, you can consider this equal to 1. Then this sigma is the stress applied on the material, square root of pi and a. A is the crack size. So in this you can get easily one numerical. One more thing here, this plane strain fracture toughness, this for that you have some condition. So that condition you should remember that the thickness required is 2.5 multiplied by K1C divided by sigma square. So this is the condition for this plane strain fracture toughness. If you have this much size of the sample, then only you can determine the K1C. Otherwise it is not means it's not possible to determine the K1C value. So for that this we have to determine the j integral, and this plane strain fracture toughness, this we can this measure through 3-point bending test, 3-point bend test, or 4-point bend test, or compact this test specimen. So these compact test specimen. So these are the 3 testing procedure to get the plane strain fracture toughness value. Next one is the critical resolved shear stress. So here you can see the formula of critical resolved shear stress. So for any kind of plastic deformation, this is the minimum shear stress required to move the dislocation. So this is tau is equal to f cos lambda divided by a by cos phi. So here lambda is the angle between the slip direction and applied stress. So this is called lambda, and phi is the angle between the applied force and the slip plane normal. So this is called phi here. So this formula is written as tau is equal to sigma. Sigma is the stress applied, cos phi, cos this lambda. So this cos phi cos lambda factor is also known as Schmidt factor that we represent as m. So this is called Schmidt factor, and this value of Schmidt factor is maximum, that is 1. So if it is maximum 1, so in that case we will get the maximum critical resolved shear stress, and it is 1 when this phi and this lambda is 45 degree. Next one is in this case is a lever rule. So lever rule is used to get the this fraction of phases present, and it is used for this binary phase diagram or ternary phase diagram. So if an alloy consists of more than this one phase, the amount of each phase present can be found by applying the lever rule in the phase diagram. So here we have this given an example of binary phase diagram. So it is a binary isomorphous phase diagram. So here we have a liquid and solid phase. So if we wanted to determine the this a fraction of liquid and solid this phase at temperature of W naught. So first we have to draw the this tie line at that particular temperature where we wanted to determine the fraction of phase. So this tie line will this construct, and it will intersect at the this liquidus line and solidus line. So the liquidus line is the line between the liquid and solid. Solidus is the line between solid and liquid and solid. So this is the solidus line, this is the liquidus line. So this tie line will cut at this liquidus and solidus. So now the fraction of liquid is the difference between the this Ws minus W naught divided by Ws minus WL, while the this fraction of solid is W naught minus WL divided by Ws minus WL, like that. So this is how this lever rule will be applied here. So for any kind of this binary isomorphous or binary eutectic or peritectic or in iron carbon phase diagram, we can easily use this lever rule to get the amount of phases present at the particular composition and temperature. So thank you so much for this. I'll come up with the this next part very soon. Thank you.